then. Okay, so there might still be some people coming in, but I'll just start. So we're getting close to the end now. Two lectures. That's Sarah. So two lectures left. Two lectures on multi-level models. So last lecture we talked about structural equation models, and I showed you how to do mediation, and I also showed you how you could use the structural equation models to combine both a measurement model and a structural model. So remember that we had something like alienation, which we didn't measure perfectly, but we had two latent, two indicators loading on this latent variable, and then predicting something else. So that's the beauty of structural equation models. So you can take some things and combine them. Today I'm going to be talking to you about multi-level models. And again, as with structural equation models, I'm not going to make you a multi-level expert. That would take an entire separate course, perhaps even a year-long course. But you should be able to apply the basics, and you should also, at the end of this, be able to understand when you come across it what people have more or less done, or sort of evaluate and say this was quite a good model or this was quite a bad model. So that's the purpose. So after today, you should be able to complete the following sections of the assignment. So it's the multi-level model, which is part of your assignment too. There's still some bits for next week, like plotting results from multi-level models. And then you're done, and you've captured everything that we wanted to do. So this is the part also where we would divert from SPSS. SPSS was unable to do structural equation models. It can do some basic multi-level models, but it can't do the more advanced things, and it can't do some of the things which I'll show you. There's some other packages like MLWin. If you're a UK student, you can get access to MLWin, and it has some buttons, and it's very, very nice, but it's not programming based, and also it only does multi-level models. It does nothing else. It's very specialist. There's SAS, there's Stata, there's HLM, but in R, again, we have many different options to achieve the same thing, so we can do multi-level models in many different ways in R. So why would you want to use multi-level? In my view, at least, group data are everywhere, so even though we commonly assume that data are independently sampled, often it's not the case. So for example, you might go into a school or a nursery and collect some data from kids, and then you go to a different nursery. That nursery might have some type of influence on the kids' scores, but you haven't captured. They're not independent because they're all part of the same nursery, so they're not independent observations. So in many cases in psychology, we'll come across these non-independent data, because for example, you might run a study, and it might be in classroom A, classroom B, classroom C. It might be clustered in a way that some researcher collected some data in Northumbria and somebody collected some data in Leeds. And so they're not independent data points because Northumbria students might be very similar to each other, more so than Leeds students. So if we compare them, they might be very different in many other aspects as well. So hopefully this will be useful for you in the sense that at some point you might come across this and you might need it. So just some examples. I've talked about children's in classes in schools, employees in departments. So if you're an occupational psychologist, there might be a hierarchical structure, and these organizations might be structured in regions. And so companies in the Northeast might be more similar to each other than a company from so if we would just not account for that, we wouldn't take into account that companies from the Northeast are more similar than if we compare to one in London, for example, or and some other aspects. We have individuals usually nested in neighborhoods, and neighborhoods are then nested in districts, provinces, or countries, regions. So you can think of it like that. So, for example, my health behavior might be influenced not just by me, but also by the neighborhood in which I live. And if we sample many different individuals, they're likely not independent. They're more likely to be similar to each other than if we don't account for this. We have individuals in couples or in families. Again, that's a non-independent structure, so we have to take into account they're part of the same thing. So you could have, in clinical settings, you could have patients assigned to the same therapists, and therapists could be nested in hospitals. So, or it could be, if you don't have a therapist, you could have patients in wards and wards in hospitals, or patients in hospitals. But the fact that they're going to the same hospital makes them non-independent. And you might say, I don't bother with any of this because I'm a cognitive psychologist, and we don't have any of that in cognitive psychology. Actually, you do, because usually stimuli are part of a set, and that set is nested in a block in your experiment in some way. So even if you think that you have perfect experimental design, usually there's some type of hierarchical structure in it, or you can think of a hierarchical structure. And definitely the more advanced experiments will have some type of a hierarchical structure to it and some non-independence. This is very annoying statistics, but it's a naming frenzy again. So many people have used names to point to the same thing, but sometimes they're slightly different. But these are the types of terms you will come across. You'll come across multi-level models, random coefficient models, mixed models to say that there's a between and a within component, for example. Random effects models, hierarchical models. So people have used many different names to point to the same thing. Yeah, and all of these, I think, can broadly put under the cluster of multi-level models. And even and so, why is this important? Very simply put, depending on the level of analysis you do, you can get very different results. So a classic example is from Robinson, who was a sociologist in the 1950s, on literacy and migrants. And you can find a positive association at state level between literacy and the amount of migrants in that state. So if you look across the 50 US states, you find a very strong positive association. Now, obviously, that doesn't mean that migrants are more literate than locals. But you would make a mistake if you were to analyze this aggregate data. You would say, and if you would draw the inference from that aggregate data, look, there's a positive association between literacy and the number of migrants. So therefore, migrants must be more literate. But that's not the case. At the individual level, the relationship might be entirely reversed. And this is a complex statistical phenomenon known as the ecological fallacy, or the opposite of it is the atomistic fallacy. So if you take it at the individual level and pull that to the aggregate level, you would have the atomistic fallacy. And so graphically, I'm not sure if you can see this here, but I've drawn here an example with some monkeys. And so if you look across the purple line, we might find a positive association between X and Y. Yeah. But within every monkey, there's a perfect negative relationship. Yeah. And for this type of situation, we need multi-level type of models to separate out the different levels of analysis. Yeah. And if we were just look at the top level, we might be telling one part of the story. If we would just look at the bottom level, we might be telling the other part of the story. Yeah. So, any questions so far? Because this is quite crucial as to why you would need it. So, there's good reasons to opt for multi-level. So, in this type of situation, we need correct inferences. As I just pointed out, it's key that you have independent observations. That's a presumption of nearly every statistical test. And so if there is a hierarchical structure, so if you didn't take into account that the kids belong to the same nursery, then you're going to be making errors in the standard errors of the regression coefficients, and you're going to be over-optimistic. You're going to say this intervention has really worked, whereas in reality, it's the hidden clustering that they all went to the same nursery. Yeah. So we need to do this type of corrections to make sure that we have the correct level of statistical significance. Sometimes we really care about group effects. Not only do we want to find out about the individual kids, but we want to find out whether it mattered whether the nursery was in a rich location or in a poor location, whether it was in London or in Newcastle. So we might have some substantive questions about the group effects of the nursery. Yeah, so we might think that the socioeconomic status or the geographical location of that nursery plays a role. And for example, in schools, there's lots of debate on like whether schools create value. So is there something like a school effect, or is it just all due to the individuals that get selected into those schools? Yeah. So what we can then do is we could address questions relating to the school level in that example, or in the nursery level in my example. So often we also want to be able to estimate the group effects together with group level predictors. So that would not be possible, because if we were to do that in just a traditional regression, because we have to separate out the levels. So in a multi-level model, we can have effects on both types of variables, on both things which are at the group level and things which are at the individual level. And so often we also might want to make an inference to a population of groups. We want to say something about these nurseries or schools in general. And again, that would be not possible, because we wouldn't be treating them as a random sample if we pull them. If we do a multi-level model, then we can correctly make the inferences that they are a random sample. And so if you get bored, I'm invested in this because I wrote some things actually about monkeys and about countries. So if you, for example, people treat countries as independent data points, but they're not. They're nested in regions. For example, Germany is much more similar to Austria than it is to Japan. And so if you were to analyze all the data at country level and ignore the fact that countries are structured in regions, you're going to be making wrong inferences. And my favorite example comes from monkeys. For example, you can think of monkeys doing nut cracking, and you might find a positive association between the amount of rain falling and the amount of rainfall and the amount of nuts cracked. But it doesn't mean that the monkeys are cracking nuts in the rain. So you would have to do a multi-level model. So if you just pulled everything, you might find at your monkey level population, it's really weird. When it's raining, then there's some more nut cracking. But what's happening is the wind and the rain causes the nuts to fall. During the sunny spells, the monkeys are cracking the nuts. But if you average all these things across days or weeks, you would find a spurious association. You would say, it looks like these monkeys are cracking nuts in the rain, which is not true. Yeah. So that's some of my investment in this. So multilevels can do quite a lot of things, but as everything, it's all correlational data, unless you did experiments, like in the cognitive psychology thing. So it's easy to mistake this first to say, oh, it is the school causing this, or it's the neighborhood causing this, or it's the region causing this. It's easy to slip into causal language. But you should bear in mind that everything is correlations. So everything is associations. Unless you experimentally manipulated it, it's going to be a correlational association. Yeah. So, as with regression, the same type of multi-level models are nothing more than like regression with some additional steps. So if you want to find out more, you need to be aware of these assumptions. You remember sort of the 4 assumptions which we had for regression. So when you want to have a stab at like what the 4 were.
There was one that was normality.
So one was normality.
Homogeneity of variance.
Yeah, homogeneity or homoscedasticity of variance. Linearity.
Yeah.
And then independence of the residual errors. So that was the 4 assumptions. You can go back over your assignments. For some shortcuts, I'm not going to hammer too much on like all the assumptions when I present you things, but you should be aware that when you do this type of models, because it's a regression, you should check all these assumptions. So many times you can say it's linear, but it turns out not to be linear because it's a count variable or because it's an ordinal variable. So you should check those type of things. So sample sizes, this is very, very difficult. So if your supervisor says, can you give me a number for we want to do this multi-level model? It's very, very difficult. So it depends on whether you're interested, for example, at the fixed level effects for the individual or the random effect. For example, the differences between schools or like these other things. So depending on what your question or your core focus is, you're going to need more at one level or more at the other level. And it also depends on the degree to which these units sort of fit nicely under this level or not. And it also depends on like some of the assumptions you make. Like, is there going to be lots of variation between schools, or is there not going to be a lot of variation between schools? Is there going to be a lot of variation between individuals, or not a lot of variation between individuals? So I wish I could tell you like the optimal number of this, but for my own research, I've sort of used a heuristic that you need probably like because it's regression, it would be good to have at least 10 observations per school or per nursery or per therapist or per stimuli set, because otherwise it's going to be very difficult to estimate any type of parameter. So there are ways in which you can relax it, like Bayesian models, which do much better when you have smaller samples, but I won't tell you too much about them. And they come with their own challenges, because then you have to make some assumptions about what is a good starting point, what is my hypothesis, all these other things. So in R, these are some of the core packages. I've worked with all of those. So you have LME4, NLME, MCMC, GLMM, and BRMS. I'm not going to tell you about these two because they're really more advanced Bayesian models, but I'm going to tell you about LME4 and NLME, which are commonly used packages. So main packages, it's up to you to pick. The codes differ between the packages. Some have some more flexibility than others. Some are a little bit easier to interpret. Again, as with the ANOVA type of situation, people have reinvented the wheel a couple of times, and every statistician might have his own little preference for one package over the other. So I'm going to give you an example, which is based on a school situation. In this case, the dependent variable is a standardized result of a student-specific exam, and it's normed, so you have their normatized exam scores. And in estimating the score in the exam, we have two levels. We have the student and the school. On each level, we have, in our example, one explanatory variable. On the individual level, we're interested in the standardized score of the student on a London reading test. And on the school level, we're taking into account the average intake score of the school, so what type of grades they take in of their students. Yeah. And if you want to find out more, you can read this paper on which this example is based. Yeah. So this is the typical type thing. So if you become an educational psychologist, you'll see for most of the things you might not see nothing else but multi-level models, because it's always individuals nested in schools and you care about their test scores. So what does this basic model look like? This is the ML ref package that has the data in it, which is this exam data. And in order to first build our very first model, we're first going to build a null model with nothing in it, and then we're going to see if we can improve, if we add things to that model which explain things. And so this is using the LME4 package, and the code is LMER, our dependent, this, and then this to say there's a school level effect. So just a vertical, what do you call it, a vertical dash, yeah? I would call it a vertical dash, yeah? And so by default, it's using restricted maximum likelihoods, and we can say that to false. The reason is because if we want to compare some things, then we want maximum likelihood rather than restricted maximum likelihood when we create these information criteria. So REML has better properties for estimating especially small samples. It applies a penalty and some type of correction. If you get larger and larger samples, there will be not much difference between REML and ML, but the default for all these packages tends to be that they use REML rather than ML because it's more conservative. So we get a bunch of output, yeah? And let's see also if I can, well, we don't have to, I think it's printed everywhere. So you can see estimates here of like a school level effect and these other level effects here. So we don't have anything there except for the intercept, which is being estimated as well. This is really our null model. And so there's not much information in it, but we really care about these AICs and BECs because those are the things that we can use like in what we did with SEM and with factor analysis. We can use it to compare to say, is this model a better model than another model? Yeah. So just I've explained this part already. So we came across maximum likelihood before. Restricted maximum likelihood might be new. RML has better properties for estimating small samples, but it doesn't allow for model comparison of these fixed effects. And so when comparing fixed effects, we would typically use maximum likelihood. And we can quantify the evidence for each model. And remember that we can also, what we can do is if we run lots of models, we can take all the AICs and rescore the lowest one to 1, well, we can basically rescore so all of them add up to 1. So basically that if you were betting, so you have 10 models, you would say I back this model for 0.7, I back this model for 0.05, 0.05, 0.05, 0.05. So in that case, you don't have to pick. So if you struggle and their models are very close, you could sort of think of it as like you're a horse racer, or like you're betting on horses, and you have 10 different models. And the question is, if you were to rescore the AIC, how much money would you put behind every single model? Yeah, does that sound sensible? So sometimes people just present the final model, the model with the lowest AIC. Sometimes they choose to present all models, and sometimes they do this weighing type of approach. So again, the best thing is to be transparent and say, I picked the lowest one because there was so much difference, it doesn't make sense to make the other ones, or to say, actually, I don't know which one is the best one, so I'm going to present to you all 3 or 4, which are quite close, and then you can make up your mind, and then you can compare the weights. What you can also do is like, if models have the same parameter estimates, you can average across those models to see if there's an effect. So suppose you have model 1, model 2, model 3, model 4, and every single one has like the same parameter. So if you average across those models, you still find an effect of that parameter. Yeah. And you can look at the Moomin package. These are things which are more advanced, which I won't do. but for you to explore if you ever have to do this. So now we built the same model, but in NLME. So you had LME 4 before, and now we have NLME. So it's losing the R, so it's LME rather than LMER. And it says, if you wanted to write out, it says this is the fixed type of component, and this is the random type of component. So in this one, you sort of have to write out and say this is fixed, this is random. Whereas the other one was a single equation where we put in with this type of thing, saying this is part of it. Yeah. And you get sort of similar type of output here with the random effects. We can actually have a look at the intercept, like 0.4142. We go back, we should get something like 0.1412 for the standard deviation type of thing. Yeah. So similar type of results, doesn't matter which package you pick, just different preferences. As long as you make sure that the estimation is the same. Actually, it's not the same here because this is REML, sorry. And it's actually very, very close, but not exactly the same. Okay, so now we're going to build up our model. So we build a null model with nothing in it, just a random intercept for school to account for the fact they came from different schools. Now we're going to add our fixed effects to see if we can improve. So stand LRT is not varying between groups. We are only looking at the individual level. So we allow the schools to vary based on norm exam, but not as a function of stand LRT. So stand LRT is at the individual level, and there's no variation at the school level. So this is a model in terminology. You might hear some people say something about random slopes and random intercepts. This is just a random intercept model. So it means that every school might have its offsets on norm exam, but there is no systematic variation based on this variable. Yeah. So when you think of a regression line, it means that the school can go up or down based on their norm exam, but the angle of it, the angle of the effect cannot change as a function of this variable. It's all parallel lines. Yeah. Does everybody sort of understand this premise? So now this is the type of write-up for the LMER. So what it's hiding at the back here is this. Yeah, it's printed the same type of output, and now we can't see the fixed estimate. So I'll open it and see if I can show to you in the output. Oh, I've not saved that output, so let's just quickly do this. Stand LRT. So this should be it. Oh. So it prints this stand LRT type of effect, and you can have you can see it's significant. So at the individual level, you have the scores they did on London reading test for the individuals predict their scores on the standardized effect. Yeah. But this model takes into account that schools vary. Oh, this is actually not the model. It's the wrong model. Sorry. It's easier if I do. I've made a mistake. I thought I was gonna. So. So I've made the mistake of not syncing this model. I'll fix it in the code. Sorry for that. I thought it would print the entire output, but it hasn't. Now you can see it. So this is the model we were supposed to look at, because the other one had like a random slope in it as well, but this one just has a 1 for school. So I've already jumped ahead. When it has a random slope, this will appear here as well. So you You can see the estimates, but what was missing from this is p-values. We see t-value, but we don't see a p-value. So I'll make sure that I fix this. So we can see t-values, but not p-values. And you can read more about why this is the case, why it's not printed, but it's statisticians have argued for a long time how to correct for the fact that things are nested, how to correct these t-values. And their consensus is that there's many different ways in which you could test significance. And one of the ways to calculate a p-value for this t-value, but you could also do it in a different way by, for example, dropping things from the model. So, and this is the recommended way. So when comparing fixed effects, we use the maximum likelihood method. So similar as we did, for example, when comparing the models when we were doing measurement invariance, we can use ANOVA to compare different type of models. And then we get this type of output. So we can see lower AIC is a better fitting model. And then we can have a chi-square test, which tells us there's a highly significant difference between the null model and the model with standard LRT in it. Does everybody understand this? Any queries? So this is probably the preferred way of doing it. So you build your model, compare it to a null model, and then you see via this chi-square test or via AIC, BEC. And I've told you around 10 units difference is already quite a big difference. And here we're looking at really, really massive differences between AIC and BEC. Yeah. And if you wanted to have a p-value, you have a chi-square and p-value for that because it's a likelihood ratio test. And so if you want to write this up in your actual report, you would say a likelihood ratio test suggested that a model with a fixed effect for the London region test was a better fit as compared to a null model. Yeah. And if you wanted to, you would actually write the equations of the regression models you did, so or attach your output. So sometimes people just want this chi-square, but you could also report the AIC and the BEC for each model, and then people can say, oh, actually, this is 200 units difference, so it must be a much better fitting model. So we can also do model comparisons to compare random effects. With caution, we can use restrict maximum likelihood. So we could see if we now allow this effect at the individual level to also allow that to vary by school. So for example, some schools might have very good teachers, and they might, for example, get your scores up quite a lot, like from the standard LRT London test. So your initial score doesn't really relate very well to your output score because the school puts in a lot of work to get your grades up. Whereas in other things, it might just be not as productive. So it's just like if you had a really poor intake score, you're going to have a very poor exam score, and the school isn't contributing a lot. So in the second model, we allow the effect of the London reading test to vary between schools. So in some schools, the effect of the test is larger, in the sense that the school, for example, is unable to get its teachers to get the grades up, and other things, it's smaller because it's a very broad, friendly school, and so it doesn't matter as much which grades you come in with. They try to get everybody's grades up, for example, and that would help. So what we now do is we built, this was the model I was showing you before, we built a standard LRT model, and we built this model, and now when we do the ANOVA, we have to say refit is false, because otherwise it will do the maximum likelihood thing. So ANOVA knows it needs to do maximum likelihood, and so it will always change it back to maximum likelihood unless you say refit is false. Yeah. So then we can see if this model does better than the other model, and you can see this is a better fitting model. So if you allow for the fact that some schools might respond differently to their students' intake scores, then you get a better fitting model. Yeah. And if we go back, you could they're not 100% comparison, but this is sort of probably also going to suggest to you that this model with a random slope might be doing better, or probably not, because yeah, you can't really compare. One is RML, the other one is ML. Yeah. So if you want to compare random effects, you would use RML rather than ML. Yeah. Fixed effects, you would use this type of model. Any questions so far? I've modeled a little bit by especially hopefully it's a little bit clear. fixed effects, maximum likelihood, random effects, RAML, yeah? And they do different things. If I get that across, I'm already very, very happy. Any questions? This is quite advanced and complicated stuff. It also trips me up sometimes. So what you would then do is we can also look at the summary, and this is what I was showing you before, but now we can see there's an estimate for stand LRT in our random effects type thing. So I won't open it up again, but this one has a stand LRT effect at the random effects thing. Yeah. I will also model the correlation between all these random effects. So if you have random effects, more than one, it will start modeling the association between these random effects. So you don't have to worry about that. Oh, perhaps I should have said in the beginning when I described the data, you have data on 65 schools and 4,000 pupils. So it's quite a big data set. So another way in which you could do this is something which is known as conditional, the conditional Aki-Aki information criterion. And so rather than using this RAML method, you can use, I'm going to call it cake, like the conditional Aki-Aki information criterion. We can call this package. We can have the conditional AAC for this null model and from this other model, and we can clearly see that this one is lower. So the model with random slope is a better fitting model than a model with just a random intercept. Yeah. We can plot this random intercept. So what does it actually mean? So it means that different schools, there's some variation. Like some schools are quite high norm exam, some schools are very low in norm exam. Yeah. You might think, for example, schools are differing in their quality, differing whether which socioeconomic environment they're operating in. So we find some variation. This is quite a nice normal distribution of the variation in the intercept. Yeah. So this is accounting again for the fact that some schools, if you were to guess how their students would do on a normative exam, you would always guess low, and for another school you would always guess high. Yeah. You can probably think of some schools in the neighborhood also where you would do the same, or like universities. Now this is a little bit more difficult to see, but this is how the relationship of the standardized London reading test varies between these schools, like allowing for some type of angle. Yeah, there's quite a lot of variation to go on. And if we hadn't modeled this, we wouldn't have accounted for the fact that some schools vary. This effect of the stand LRT will vary between the schools. Yeah. So now we can have a model with a random slope and a fixed effect. And so we now have stand LRT as a fixed effect model, but also as a random effect thing. So we allow it to vary between schools, but we also allow for the individual level. So this model allows the effect to vary as a function of schools, but it still allows us to also look at the individual level to see if there's something going on. Because it could be that when we initially built this model, we're just looking at differences between schools, and we were over-optimistic in what the stand LRT effect was. This was the one I was showing you erroneously before, but I'll open it now. So that's the stand LRT class, and in this case, it's printed this out. So in this model, we still have our random effect, and now it's printed some p-value, and it's because I attached a package to it which does it for us. But I'll tell you a little bit more about that later. So because it's using LMER Multilevel test, and then it will automatically print p-values, even though most statisticians wouldn't want you to do that. They want you to use the likelihood ratio method to do that. Because it's very easy to then start looking for, are these parameters significant or not? Yeah. So we find both, we find an effect at this individual level of the London reading test scores, above and beyond the differences between schools on how their London reading tests scores influence their normative exam scores. Everybody still with me? It's quite complex stuff, perhaps, or am I saying it's easy? No? Okay, we've covered quite some ground already. So this is just the power of these multi-level models. So you can partition out and you can look at the group level effect, and you can also look at the individual level effect. Because you remember, with that plot, we could see at what stand LRT does between the schools, but we could also look at what it does at the individual level. And with a normal regression, you wouldn't be able to do this. So that's why this is important. This is why you want to look at this. So it is also possible to enter group level variables as well. So here we will add a predictor that indicates the size of the school. So it's important that the variables are the same length as the variables of the individual level. So that means for every, so you'll have lots of the same values because it's the same pupils in the same school. So your data really has to be the long format. So every single data point is an individual, and then there will be some values which are the same for all individuals because they all went to the same school. Yeah. So for every unit on the lowest level variable indicating school level value, so the average intake tests for every school. Yeah. And so that's supposedly in some way related to their size. Yeah. So this is a model where we now have what we had before, but we also have the school average test like this scav thing. Yeah. And so what we can then do is we can see if that matters. I'm going to open school average thing. And you can see we still have our individual based effect of the scores from the London reading test, but we also have a school average effect. Yeah. So if the school is taking in on average better grades, they also do better on the normative exam. Perhaps unsurprising. Yeah. But the nice thing is we've had things here at both levels. Again, something which we couldn't do with regression. In regression, we would have likely done a regression for all the schools and a regression for all the individuals. And here we have one model which correctly accounts for the fact that individuals belong to the same school, if they belong to the same school, and that schools might be different from individuals. Yeah. So, and again, it's quite impressive. So perhaps we shouldn't be paying too much attention to the significance levels because you do have 4,000 individuals. So you could say it has to be highly significant, not just 5%. But this still looks like a very reasonably strong effect. Yeah. If we look at the p-values, at least. Okay, so in this model, we both have something which is at the individual level. We have a random effect at the school level, accounting for this individual variation, and then we have something at the school level. Yeah. So I've been blabbering on for a long time now. You're going to do the same, but with Scottish schools. So you're going to have data on 3,400 Scottish secondary school students, and they take some standardized tests at age 16. And both the primary school and the secondary school that the students have attended have been recorded. And I would like to test a null model, so just a random intercept at the secondary school, and attain as the dependent, so that's their score on the standardized tests. And then you would like to have a model with like the fixed effective verbal, which is their score on some verbal tests, and a random intercept at attain as a dependent, compared to the null model. And then you can export results like building a sink, like we did. And I would like to build a model with a school level and a slope for verbal and attain as the dependent and compare it to the null model. Yeah. And I'd like you to also make a plot like I did, like this type of plot of one of the random effects. Yeah. So similar to what I did, but just with a different type of data set. And I'll be around and Sarah will be around to do some troubleshooting.